Okay, that's good. I hear you very weakly, but I got this was affirmative. Anyway, if you can't hear me, you will stop me, no doubt. Good. So first of all, I apologize that
Jacques,
I cannot be. Yeah.
Sorry, because the microphone was not working. Let's start again so I can introduce you.
Oh, okay. Yes.
Sorry. Let's start again. So let me welcome the last speaker of this part, let's say, which is as well from Belgium, from the University of Antwerp, Jacques Tempere. So Jacques, the floor is yours.
All right. Thank you. So yes, first of all, let me apologize for not being present in person with all of you. And I would, of course, also like to thank the organizers and especially Professor Fomin for nevertheless giving me the opportunity to present some of our work here. So I'll be shifting gears a little bit, and I will be talking not about Cooper pairs in solids, but Cooper pairs in atomic quantum gases. And I'll begin my talk by trying to explain to you why these quantum gases are good quantum simulators for nanoscopic superconductors, especially given some recent breakthroughs in confinement and manipulation of these systems. And then in the second part of my talk, I'll say a little bit about polaronic effects in these systems. And then in the end, I'll try to bring it together to tell you why I think these polarons are interesting ways to probe nanoscopic superfluidity. Good. So since perhaps not all of you are very familiar with the quantum gases, let me remind you quickly about the timeline for these systems. So on the picture on the left, you see an experimental setup, and there's a little blob in the center. That's sodium atoms that are trapped, and they can be cooled down to nanokelvin temperatures. And when they are cooled down, then they can reach a Bose-Einstein condensation. And this was first demonstrated in 1995. It took a little while to show a pair condensation of fermionic atoms, because the fermions are harder to cool down, basically. But nevertheless, this was demonstrated. And then shortly after, it was shown that this pair condensate of fermionic atoms was also superfluid. And this was done by rotating the system. And if you rotate it, then you see a lattice of singly quantized vortices nucleate. And that's really the smoking gun proof for this superfluid. So why are these things good quantum simulators? Well, basically, that's because there are many parameters of the system which can be controlled to a high degree and tuned very, very well. Maybe the most well-known of these parameters is the interaction strength between the atoms. So you can actually bring this system in a regime where the fermions form tightly bound pairs. And then these pairs are like bosonic point particles. They will undergo Bose-Einstein condensation. And then you can tune the interaction over the unitary regime into a regime where you have weakly bound Cooper pairs and a BCS type of superfluid state. But there's more than that. You can also tune the geometry, the dimensionality of the system through this confinement. I will come to that in a minute to tell you a bit more about that. But there's many other knobs. There's, for example, the spin imbalance that you can tune. So you don't need to have an equal amount of, let's say, spin up and spin down pairing partners in these systems. And if you can think of this one as an artificial Zeeman field, maybe that you add, then you can also add spin-orbit coupling to the system. And moreover, you can make the strength of this spin-orbit coupling tunable. And so people have been using this to try to create exotic forms of superfluidity in this system. So if you think of the spin imbalance case, then you can try and create the FFLO state. Whereas if you add in also spin-orbit coupling, you can start looking for topological superfluid states. right? But let's first turn a little bit to this confinement, because I want to tell you what's nanoscopic about these systems. And for that, I have to look at the relevant length scales of the system. That's the coherence length and the correlation length. Correlation length you can think of as the size of these pairs, and the coherence length that you can think of as the typical distance over which the pair condensate can heal or can change when you put an external potential in. And well, you see this correlation length nicely goes down as the pairs get more tightly bound. That's the red curve. But if you look at the maximum of the two, then this does not drop much below 1 in these units. And these are units determined by the Fermi wave number, which is for these systems typically on the order of inverse microns. So the effects of confinement, so when confinement will start to modify the superfluid properties, that's really on here the 10 to 100, or 1 to 10 micron scale. So it's a few orders of magnitude larger than what you have for the solid state superconductors. And in fact, most systems are already in this regime. It's kind of hard to look really at bulk type of superfluidity. But there's more. There's some recent breakthroughs in how we can trap these systems. And one is the BEC on a chip. So there, in addition to the externally applied magnetic and optical trapping fields, there's also the field that comes from the circuit that's drawn on the chip, so from the leads on the chip, which influence the trapping potential. And then you can, by drawing a circuit on your chip, also make a circuit for these condensates and these gases. So here's an example by Mukuri et al., where you have both condensates that's being wound around each other, and this is being used as a detector of rotation, a very sensitive detector of rotation. And the other technology that's basically the same as you have here in the room, an overhead projector, where you have lots of digital micromirrors that you can tune, or you can achieve the same with an acousto-optic deflector. What you have is a laser beam that scans on a scale that's very faster than any other scale, and with that you can really draw potentials. And people have been making nano rings, if you wish. They are micro rings, but they are nano rings for what the condensate is concerned, nano squares, or a pearl necklace, or all sorts of other configuration that you can make. Because I knew that, or I suspected that the previous lecture would indeed be about cylinders. Here we also have a cylindrical type of confinement. Here the atoms, so it's blue detuned laser beam which repels the atoms, they're confined inside. But if you use red detuned light, then you can try to make a cylindrical confinement where the atoms go towards the edges of the cylinder. And people have been doing all sorts of funny stuff with that. So here you see a Bose-Einstein condensate that's subjected to a potential in the shape of Bose and Einstein. So indeed, lots of different ways to manipulate these condensates, both playing with the confinement as well as trying to play with the type of superfluidity that you have by adapting the parameters. So let me now go to the second part of the lecture, where I talk a bit about polarons. And well, you're probably aware of the solid state polaron, which is an electron put in an ionic or polar crystal, and it deforms the crystal lattice, and the electron together with the lattice deformation forms the polaron. So that's described by the Fröhlich Hamiltonian that you see here, with the term for the electron, a term for the bath of bosons, where the frequencies here are the LO phonon frequencies. And then there's the interaction that basically tells you that electrons can emit or absorb a phonon with a certain Fröhlich amplitude V of k, which goes like 1 over k and is proportional to a constant alpha. So the remarkable thing is that if you place an impurity atom in a Bose-Einstein condensate, that system will also be well described by a Fröhlich Hamilton, at least that we copy. So there, now the bath of bosons, you have to be careful. It's not going to be the bosonic atoms. So here, if I place a potassium impurity in a rubidium condensate, the bosons that we talk about that will dress the impurity are not the rubidium atoms. Rather, they are the excitations of the superfluid. So here there will be the Bogoliubov excitations of your superfluid. So you have to replace the typical frequency of these guys by the Bogoliubov frequency. You see it starts as a sound mode with velocity c, and then around the inverse healing length, it turns over more particle-like. Note that the interaction strength here is no longer going down as 1 over k, but for large k, it's going to a constant, and so that will need some renormalization. So we've been extensively studying this system from 2009 till 2013 with the last publication in 2015. And this is mainly the work that was done in collaboration with my PhD student at the time, Wim Casteels. So if you want to know more details about that, you can don't have to download the individual papers. You can simply download his thesis. It's very well nicely written up in there. So 2015, it took, there were no experiments then. The first experiments came in 2016 by a group of Debijin in Gila and Jan Arlt in Aarhus University. So how did they do that? They started, so this will be the experiment of Arlt. They started with a Bose condensate of potassium-39 atoms in a state that we label state 1. And then with a radio frequent pulse, they are going to do a spin flip and flip this to another state, the M0 state, here indicated by 2. And normally you have to pay the Zeeman energy for that. But if these impurity atoms form polarons, so if they start to dress themselves with the excitations of the superfluid, then the energy will be shifted by the typical polaronic energy shift. And this energy shift is something that you can measure, or at least that they attempted to measure. You see, the green wiggly line doesn't all the way go down to 0, it goes to some curve here. So I'm going to be focusing on what happens to the right-hand side on the repulsive polaron rather than on the stuff on the left-hand side. So here you see the experimental results. It's a little bit messy, but you can see the trend. And so if we put some theory there, then that's shown here on the right. So the diamonds are diffusion Monte Carlo calculations by Luis Pena Ardila. There's some other curves there that are variational Monte Carlo things, and the circles are the experiment. See, the experiment is a little bit messy. There's different ways to extract this data and get the energy shift. There seems to be a systematic shift upwards there. But the bad news for us was that, well, this black curve here was our theory. So it's nice, it matches nicely when there's a weak coupling, so on the right-hand side of the part, but then it comes kind of crashing down. And since we very much like the Polarons and Feynman's approach, we tried to figure out what was wrong and had to do several corrections. First of all, when you get to stronger coupling, now you have to add new terms to the Hamiltonian beyond Fröhlich terms, which involve an electron that interacts with 2 of these Bogoliubov excitations. And then that didn't turn to be enough. We also had to improve the approach that was developed by Feynman for the original solid state polaron. And the main improvement here was to generalize the memory kernel. So in Feynman's model, you represent the phonons by a mass attached by a spring to the impurity. And this gives you a retardation interaction between the impurities that's dominated by a single frequency. So what we had to do is generalize this to this memory function, memory kernel X And rather than having M and W, two variational parameters, we now had to do a functional minimization with respect to the memory X. That work was done by another PhD student, Timur Ikhmukhamedov, and also led to a series of papers, which in the end became his PhD thesis. So let me show you the results now, and it's already looking much better. So the diamonds are still this Monte Carlo results that we wanted to get closer to. The blue line here is a renormalization group developed by Grust, and this is also Daimler and co-workers. Mean field is like a Lilo Pines thing that we know is going to fail at stronger coupling. So that's nice. And if I superpose or try to superpose on this the experimental data, you see that the trends are there. But still, as we know from before, this experimental results are a little bit above the Monte Carlo data, which you can see even at rather weak coupling, so upper right-hand part. And since Monte Carlo is supposed to be exact, there must be something that is not taken into account there. We thought about it, and our suggestion for that is that it's an interaction shift, because there's really a very high density of impurities. They don't just make one impurity in the Bose-Einstein condensate, but they put a lot of these impurities there. And so you can have things like bipolaron formation, tripolarons, or in interaction, many polaron physics. And indeed, if you would look at the bipolaron problem now, this is the red dashed line here, it seems to lie much better with these experimental points. But this is this is preliminary. We still have to refine this part, but we do think it's due to the interaction part. Okay, so now I told you about these interesting superfluids and about the polarons. So I want to bring them together with something that we now plan to do. And that's bring these polarons from impurity in a condensate towards impurities in superfluids, exotic superfluids, and confined superfluids. So we started out, if you wish, on the right-hand side here, on the BC side, where this red line, the Bogoliubov spectrum, is the main fluctuation present, and the impurity interacts with that. Now we want to bring it to the BCS side, where there's a lot more fluctuation. So this Bogoliubov mode is influenced by a pair breaking continuum that will be there. There is a Higgs mode on this side. And there's people have been looking at these modes, as you can see, with a lot of different work, both in experiment and theory. There's one particular work that I would like to draw your attention to, and that's our work, which will be presented by Sergei Klimin at this conference later this afternoon at 17:40. So we also calculated this kind of spectral functions, in which we can find that there's lots of different modes that will start to address the impurity. And so the idea is, of course, to look also at this, at whether we can use the impurity to see these kind of modes and to determine what superfluid phase we are in. So this is going to be a part of the work of a current PhD student, Laura van den Bremen, whose work it is to go from the BC polaron on the right-hand side of this graph at the bottom, more towards the left to the BCS polaron. And then I also want to draw your attention that these impurities can be subjected to their own confinement potential. So they can be localized within any other shape that you are going to create for these superfluids. And they can be a local probe of the excitations of the superfluid, and hence of things like the pair density, etc., etc. Good, I think I've used up my time, so I will finish there, and thank you for your attention.
Okay, thank you, Jacques. I hope you hear me.
I can hear you.
Okay, great. That's already a plus. So it's time for questions. So the floor is... Yeah, so if, let's say, then I can take the word, I can ask a question. So,
Sure.
Jacques, the first question, let's say, which for me was, because you say the tunability of this type of, I mean, I'm completely out of this topic, let's say, from experimental point of view, but how, can you comment, how do they induce the spin-orbit interaction, how this is done?
This is done basically by coupling the atoms to a laser field, which will impart a momentum spin dependently. So the laser field gets, so you absorb from, it's actually a Bragg scattering kind of thing. So you absorb from one laser beam to the other laser beam, but the beam couples it couples differently to the different spin species. So basically your spin up atoms get a kick to the left and your spin down atoms get a kick to the right. And if you go back to the spin orbit coupling thing, and then you can see the dashed blue and the dashed red line are basically these kicks that you can give.
Okay.
And then because they interact, you get effectively, if you write down now the single particle Hamiltonian, you will get a spin orbit coupling.
Okay, and then perhaps let's say also a final question, because we also have to take the coffee break, but is related to, I mean, making the potential on the one which was on your conclusion slide, which is the fast laser scanning. So, so which is here at the right, all these beautiful, let's say, what is the time scale you need to do that? And actually, can you really say then, I mean, that this is a uniform potential, or the dynamics is important, and can they even play with the dynamics?
So you can play with the dynamics, but you can draw much faster than that these condensates can respond. So the speed of sound is let's say, what you would have to look at. And this is rather slow. So it's on the order of, so from on a micron scale, it's milliseconds. And so you can make these devices that will draw much faster than milliseconds. Right, your screen is updating. A good screen is updating at 100 hertz, so once every 10 milliseconds, and that's usually a much more complicated pattern to draw. So yes, that's what we can do. Let's say the kind of more limiting thing is how finely they can focus it. So you have to be able to focus the thing also smaller than these two length scales that I showed you, these two guys, right? And so that's kind of on the edge. So the edges of our potentials, we can try to make them sharp, but we will not make them completely sharp. And maybe I forgot to mention one of the most important things, but it's rather fresh news. So we work together with University of Ghent with a group of Karel van Akkoleijen, who now have, since a few weeks, we have our first BC on a chip, which we will be able to combine with this acousto-optic deflector method to draw potentials on these things. So we're looking forward to doing that. So we just have reported, let's say, the realization of Bose-Einstein condensation in the tab, which is the first step, cooling down the atoms to making them cool enough to see this PC. Okay,
thank you, Jacques. So let's thank the speaker and also all the speakers of the session.
Thank you, and goodbye, everyone.